Yes. So we'll continue now with part 2 of Akshay Rana. Right.
Okay. Welcome back. So let's start.
Yeah.
Okay, so are we here? Please. So now, last session we ended with this particular slide where I was telling you that you end up with a function like this. This was nothing more. It's the multiplication of all the PDFs. Please settle down. So this is the multiplication of all the PDFs. This is a kind of a joint probability distribution function. We are naming it to be something called likelihood. We are naming it to be likelihood. And our aim is to find out the maxima corresponding to it. We want to find out the value of parameter A and B, which are going to maximize it. That's the problem. Now we will focus on this problem only. Eventually, this is a diagram like something which you can see. Okay, it's like you have a 3D, 4D space which might be having its local maxima. You can see this is a peak over here. It's just a visual representation mimicking the behavior. But eventually you want to go to the peak. You want to reach to this particular peak. There can be multiple ways through which you can start. So you standing here, you might think, okay, I'll go this way or that way. So there are multiple ways through which you can start. This one again is 3D, because we are in a 3D world. The moment I'll start talking about 5D, 6D, that is going to be more complicated. Okay. So now the approach that I have named is Markov-Chain Monte Carlo. Yeah. So Markov-Chain Monte Carlo method, which I'll be talking about, can be divided into two approaches. I'll talk about, the whole analysis is going to be, now try to see the broader picture. You have data, you have certain model, and now you have a statistics. The way you are going to treat this data and model, the way you are going to treat and find out certain analysis through or certain inference through it, the method, name of the method is going to be Markov-Chain Monte Carlo. But the way you are going to interpret this particular data, what kind of information you are going to have about your distribution, the way I told you that we are considering all the data points are Gaussian. If you have any prior information about it, I'll talk about priors and everything in detail. Then if you are going to, based on all the information that you are having about data, if you are building your problem, that will come under the preview of Bayesian statistics. So Bayesian statistics is a problem of getting the distribution, okay, and now reaching to the maximum of that particular distribution. That's a problem of statistics that we are going to deal with the Markov-Chain Monte Carlo. So right now in today's session, I'll will talk about the statistical part. Bayesian aspects, when we'll be dealing with the real data, will come on to the Bayesian part later. Okay, are we making sense till now? Yeah. So now, so that's why I'm not talking even about the Bayes-2 right now. Those of you are familiar with Bayes-2, I'm just going to talk about Markov-Chain Monte Carlo. Even when I'm talking about Markov-Chain Monte Carlo, it is having two terms. One is Markov-Chain, another is Monte Carlo. I'm further going to divide it. I am firstly talk about the Monte Carlo. What do we understand from the Monte Carlo method? Okay. So I don't know whether some of you might have done it. Have you ever tried to calculate the value of pi by using the Monte Carlo method? Anyone who has done it? Calculating the value of pi by using any numerical method. Okay, let me just try to give you a brief overview of the thing. So in general, when we do talk about, that's a very simple way of understanding Monte Carlo. One is the easiest problem, that's why I'm starting with it. Later we'll do the advanced versions of this as well. So if you want to calculate the value of pi, then what we can do, we can assume a particular square. Okay, let's say we have a square. Within that particular square, I can draw a circle. Let's say this is going to be, radius of circle is going to be r. Fine. This is a structure I have created. Now, what I am doing, when I am talking about Monte Carlo, what I am trying to say, I am throwing certain dots. Let's say all of you are having a chalk. This is a diagram all of you are having, and all of you are having a chalk in your hand, and you are throwing that chalk on this particular curve. So obviously, and you are making sure that it's going to lie within this particular region only. Now, if each one of you are working independently, you are not correlated. Obviously, you are not. Your throw is not going to be dependent on the other's throw. One condition. Secondly, you are not biased. You are not biased that I'll throw it on the center only. If you are not biased in the sense that I'll choose that corner only. If you are kind of unbiased about that, you are randomly throwing it into the whole region. What I'm trying to say, I'm saying if you are choosing a uniform distribution to throw all the chokes, the whole area enclosed by this particular square is uniformly probable for you, and you are throwing the chokes. Let's say 100, like 50 of us are here, you will keep throwing it. Eventually, if I throw hundreds of chokes or hundreds of those data points, this whole space will kind of get filled if I am throwing them uniformly without having any prior bias, choosing the corner or choosing a particular center or somewhere. Okay. Now, this process of throwing these random points, this process in brief, I can say, this process is known as the Monte Carlo. Just try to understand. Only the process of throwing these chokes. Okay. If you are choosing a particular distribution, if you are choosing the core, like I'll throw the chokes on the center only, then you are choosing having some distribution in your mind. So that can be a Monte Carlo corresponding to a distribution. But if you are the whole space is uniform for you, you are not biased upon a particular region, then what you can say, this area is uniform for me, then you can say you are throwing this Monte Carlo with uniform probability. Okay. Is it seems simple or understandable to everyone? Now I'm saying I can calculate the value of pi by using it. So what I'm doing, I'm throwing these random points. Let's say let me choose some. Let's say like this. All of us are throwing. Okay, I fill this one, and I'm assuming these are going to be uniform, and then I'm filling this area with like this. Okay, these are the chokes we are throwing. Now, what I can say, if I throw a significantly large number of chokes, if I'm throwing significantly large number of chokes, then the whole area will be covered by this particular those chokes. So I can say the area enclosed by the circle is going to be proportional to the number of chokes within circle. I am calling them the chokes which are inside the circle. I am defining them to be NC. And area enclosed by the square can be proportional or will be proportional to number of chokes within the square. Is it fine to assume if it is filled uniformly? Then if it is the case, then removing this proportionality relation, what I can say, area of circle, can you tell me what is the area of circle for this one? Pi r square is going to be divided by, what is going to be the area of the square? 4 pi r square, because the length, one side is going to be 2r now. It is going to be equal to NC divided by NS. What is NC? NC is the number of dots that are going to lie inside the circle. NS, the number of dots inside the square. If I write it down, so I can say the value of pi is going to be 4 times NC divided by NS. So the task is simple. You have chokes, you are throwing them. You are just counting how many chokes are lying inside the circle, how many chokes are total chokes you are throwing, which are lying inside the rectangle. You count the number of those chokes, multiply by 4.
So there will be pi in the.
Sorry. Yeah. There is no pi, obviously. Otherwise, sorry. Okay. So yeah. So r square I am cancelling out. So that's how you are calculating. Now, is it clear? Now let's try to see whether we are trying to get something of this sort. So if you go through this program, I am doing this very simple program. If you'll see, can you see it? So I am defining certain parameters, a circle, and there are these x, y, these are the sides of the circle. Then throwing the uniform random numbers. Do you know how can we generate the uniform random numbers in the Python? There is a library called random, and you can use the random dot uniform. How can we generate Gaussian distribution? That's random dot normal. In tomorrow's session, I will try to cover in case you want to create a distribution which is not known and which is not even defined in the Python. We will try to understand, can we write down our own code to create the uniform random numbers coming from a given distribution. But right now I am using a library through which you are creating the uniform number. One exercise which some of you, like if you are interested, you can note down. Even the algorithm, even if you start with any programming language, you start with Fortran or C++, or Java, Python, or any programming language, for creating uniform random numbers, they have an inherent library defined. Okay, the algorithm that do create uniform random number is the LCG algorithm. Note it down in case you are interested. Linear congruential generator algorithm, which help us to create the uniform random numbers. And these random numbers are not the real random numbers, these are pseudo random numbers. Okay, what do you understand from the random number? When you are throwing a random number, if I am saying I am creating a pool of random numbers, that I am assuming that each and every number is completely random, they don't have any correlation, any bias, any input, they need to be very independent to each other. Like the phenomena of radioactive decay, you have so many atoms inside a radioactive material, but you don't know which nucleus is going to decay the next moment. That process is completely going to be completely random. Okay, but when we try to simulate that same phenomena in our computers, then we use certain algorithms, and algorithms are going to be based on certain inputs. And because you are giving some inputs and then getting certain random numbers, then obviously those random numbers are not going to be pure random numbers. That's why through machines till now it's not possible to create pure random numbers. We are creating the uniform random numbers. But with the emergence of this quantum computing, now we are having some hopes that we are having the chances to create these pure random numbers as well. Okay, but
these numbers are still positive and integer.
Yes, ma'am.
So they are not exactly random. Yes.
So now I'm doing the same program. I hope you will go through. If you know the basic terminology, basic syntax related to Python, you can create all these circles and everything. I'll give you the code. You will go through it, play with it, try to understand it. But what I want to focus on, I want to show you this particular diagram. What I am doing, I have drawn a rectangle, then a circle. I was throwing this particular dots. I have written down a program in which I am just counting now, counting the number of data points which are inside the circle. I am counting them, and then I am counting the total number of chokes or those random points I am throwing, and I am putting it in that formula 4 times NC divided by NS. So if you'll see the formula, I must have written. Yeah.
Can you zoom it?
Yes, ma'am. So you see, this is just simple if else loop and other conditions. Okay, so now what I'm doing, 4 times inside circle divided by total numerical sample, how many dots you are throwing, and if you try to calculate, the value that I am getting is 3.116. This is not correct value, obviously. This is an approximate value. What can you do to make it more accurate? The same frequentist kind of approach, you will increase the number of data points. When the number, I might have thrown roughly around 10-20,000 data points, but if you throw these numbers in millions, then your result is going to have less and less error, and you will be getting an exact value of pi. That's going to be the way we are calculating the value of pi. Now, why I am trying to do this particular exercise, just to explain you what is Monte Carlo in it. So in this whole problem, Monte Carlo was to throwing the points on a given distribution, a given region, or a given space. Okay, so it should come in your mind. There are some mathematical explanation, but for a broad sense, we can conclude it in that manner. Okay. Now I am going to give you an exercise for all of you. Now try to do the same problem, try to solve it. You can write down your own program taking reference from that. Now instead of considering a circle inside a rectangle, now take a sphere inside a cube, and now try to calculate the value of pi by using it. Okay, formula will change, but that's a homework for all of you. Just try to figure it out. How will you write down your own program, that will give you the clarity for the previous program as well. Okay, are we good till this point? Anyone having any question? Yes, please.
So like you said, uniform random variables.
Yes, uniform.
Random variables is understood. What
Okay. So see, when we are creating random variables, random variable might be coming from some distribution. So if I am having a particular, when I am saying uniform random number, let's say you are having a choke. Okay, I am saying this region you are supposed to throw that particular choke. When you are throwing the choke, if you are having that the each and every point on this particular desk is, you are having giving uniform probability to each point, that if you throw it there, if you throw it there, each point is going to be uniform for you. You are not biased towards it. Then I am saying that this whole desk, whatsoever choke you are going to throw, those chokes are going to be random numbers because you are throwing it randomly, but they are going to follow a uniform distribution. That's why I am calling them uniform random numbers. But now let's say I'll give you the choke, and you are not liking my lectures, then I'll give you the choke or some X or something, and you are supposed to throw it. So obviously you'll not throw it there. You'll not throw it there. You'll either throw it on me, or I'll in case I'll escape, you will throw somewhere around me. Then what will happen? You are throwing it randomly, but you are having me on the mean. So you have a particular focus on me. I'm going to be mean. The area is going to be my variance. Then again, the 50 random numbers I will be receiving, but that 50 random numbers, they will be coming to me. I'll be in the mean corresponding to that. If the distribution is going to be, let's say you plotted it like throw it in a manner binomial, in that case, if large number, that would be a Gaussian. Okay, so those will be the set of random numbers, but that will be random numbers, normal random numbers. Okay, so when you create random numbers, you have certain distribution. I have told you about LCG algorithm, that is for creating the uniform random numbers. But later tomorrow we'll see, if you know the uniform, how can you create, let's say, binomial distribution, Gaussian distribution, some beta distribution, chi-square distribution. We will try to do that tomorrow.
So in this case, it either hits you or it doesn't hit you. That's why it's binomial.
It's no sir, it's not like I'm just this is the whole area. I'm pointing, if some choke is here.
Not in your
In binomial it's
which we are throwing at you, that is either hitting you
or not hitting.
so then
So it's a binomial. But if I'll say this is the whole region, and if I am saying even if you are throwing it, I'm giving it a particular point. Let's say if I hitting me, I'm sitting on the mean. This is my mean. If it is hitting me, this is the mean value. If it is here, this is coming with some error. So corresponding to this mean, this is the associated error. So then you plot it with certain error. So then you can call it a Gaussian. But don't try to do that. Okay. Anyway, now let's get back to the stuff that we were doing. I diverted the whole discussion from this point to defining the Monte Carlo. Okay. Now I am going to use, how much time do I have now? Okay. Now what I want to do, I have just 1 second. Yeah. Now what I want to do, is it visible? This distribution. Now I have told you that my aim is to define a likelihood or a distribution and then find out the maxima. And over there I was defining many summations and a lot of things. I just want to simplify it. I want to solve a problem which is this is a PDF, probability distribution function. Have a look, it's not e to the power minus x square, along with that you have some sinusoidal terms as well. So obviously it's not Gaussian as well. So now you have a distribution which is not Gaussian, and if we plot this distribution, I'll show it to you. If you plot it, you will be getting something of this sort. Okay, this is what you are getting if I'll plot it. Now it is 1D. There is only x parameter, so that's why 1D I am trying to solve. Later we'll do it in 2D, 3D, 4D. Okay. Now what I want to see, if I can plot it, then I want to write down a computational algorithm by using the Monte Carlo method in such a way so that I can approach to this particular maxima. Okay, so I'll try to do it in a manner which is going to be useful for us. Okay, now let's try to talk about how I am going to approach this particular problem. Let's focus on this. Okay, is it clear? So what I'm doing, I'm going to draw a, just 1 second. Let's say we are having a distribution, something of finite. Okay, so I want to talk about a algorithm called acceptance rejection. So if you'll see over here, I am plotting the values of x. Over here, I am plotting that probability distribution px. Yes. Now, if I want to use the Monte Carlo method, I have told you the Monte Carlo means you are throwing a chalk. Yes. I am assuming that all of you are having a chalk and you are throwing it, and first chalk anyone of you can throw it. So I have chosen, let me choose another color. Let's say I have chosen that chalk, the value of x over here. So every chalk would mean one value of x. It can be anywhere, and if I am throwing it uniformly, it can go anywhere. I have chosen intentionally to be there just for the, because it's random, it can go anywhere. So I have made this chalk. Firstly, I am throwing with this. Should I zoom? Okay, I am throwing it here. The moment I am throwing it here, eventually what is my aim? I want to approach to this maxima. Yes, I want to approach to this maxima. So this is my first point. I am saying it, I am corresponding to this. I will name it P naught. The probability, if you know x, you can find out the P naught. Now, what I'll do, I'll ask the next person. I'll ask the next person to take another chalk and throw it. Obviously, but now what I'm asking you, throw it in a manner that it is somewhere around it, like either this side or that side. Okay, choose, keep it in the reference. Now, some of you might, if it is going to be completely random, one person might throw it here, one person, third one I'll ask, someone might throw it here. So I don't want that. Now I want to ask you, throw a chalk. So remember, let me just see. When I was throwing my first chalk, what I was saying, I have chosen it to be randomly. You throw it randomly with uniform distribution. Now what I'm saying, I'm asking you, you are throwing the next chalks, throw it in a manner that it is kind of having this as a mean. Like say I'm considering it, okay, let me plot it. If I'm saying this is the mean value, this is the mean value here. I'm plotting it Gaussian kind of curve. It can be anything, but for now, let's take it to be Gaussian. I'm saying next random number that you are throwing, that should be such that it is having the mean of the mean value as the previous point that you are throwing and the certain variance. So this variance can be anything. Okay, just forgive me for my drawing. Okay, so this is the error. So input is going to be your mean, variance you are going to choose. Now, if I am going to ask throw the next random number in this manner, then obviously either it is going to be closer to this point, somewhere here either or here. It will not be over here. It will not be here. Reason being, because this is a Gaussian distribution. If you go very far, the probability will be very zero. It can be, but it's not exactly zero, but asymptotically it's going to approach zero. So now next point that you are throwing either will be in somewhere closer to this one. So there are two probabilities. Either your point is going to be this one over here. I'm calling it x1 if this is x0, and or it can be over here. There are both the probabilities. I'm calling both x1. Okay, just x1 or x1 prime, let's say. Fine. In the acceptance rejection algorithm, because my choice is that I want to approach to the peak, my aim is to approach to this x best fit. My aim is that. So if the point is going to be in this direction, where the probability over here corresponding to this one, if you calculate the probability, this is the distribution is going like this. If you calculate the probability over here, this is going to be P1. If your probability P1 is going to be less than P0, the previous point that you have thrown, then you are going to reject that x value. Means the point that you are throwing, if the probability it's going on a downhill, if it is not accepting, then you will reject it. But if P1 is going to be greater than P0, if P1 is going to be greater than P0, then what will you do? You will accept it. So the moment you will accept it, you will come somewhere here. Now what you will do, you will draw a different Gaussian over here, and I'll ask you to do the same job. If it is going into the negative direction, I'll reject it. If it is going into the positive direction, I'll accept it. What will eventually keep happening? If we'll keep repeating this exercise again and again and again, it will eventually reach to the maximum. And that's why if you will keep repeating this exercise for extensive number of points, you will realize that the maximum number of points they will reach on the maxima and they will stuck over them. Okay. So this algorithm is known as the acceptance rejection method. You will start from anywhere keep rejecting the point if you are going away from maxima, and but keep accepting if you are reaching towards the maxima, and you will keep doing this exercise. But can you see some problem with this particular approach? Yes, please.
Sir, if we compare it, if we think it to be reflecting problem, it will get stuck at that top. Suppose if we have some higher point over there, it is solely dependent upon your initial data point.
In the initial data point. That's very good. So see, that's why I have chosen this particular plot. Now, because first point I am choosing randomly, so that's the initial value. Why I am choosing it to be here? Think about that value to be here. Yes, if this value is over here, you are writing down the algorithm, and eventually you will reach somewhere here, and then after that you will stuck, because you will not be able to go down here, because this your algorithm is not allowing you to go into this region. So eventually, acceptance rejection algorithm is not a very good algorithm. Reason being, it's not going to handle all the local maxima and minima. The moment you start working with this particular algorithm, it's going to stuck somewhere in the local maxima, and then you will not be able to reach the you are not going to reach the absolute maxima or the global maxima of your distribution. Okay, so this is a problem with us. Now, how to resolve it? Resolving it comes through a process known as the Metropolis hasting or Metropolis algorithm. So Metropolis provided one solution to this problem. That's just the increment thing. Same thing will be doing. Okay, so I'm going to plot it again. Same distribution, something like this. Now this time we understood the problem that we are stucking on a local maxima. So now what Metropolis suggested, the suggestion is, let's say you have chosen your point to be somewhere here. This is your x naught. So now let me just give you the names, because then I'll be using those words right now, otherwise I'll say keep saying x naught. The first point that you are going to choose, that point is known as the initial value. Okay, obviously first point, because you are choosing it randomly, it can be anywhere. Okay, second, the term that you are using, I am using when I want to throw the next random point, then when I am throwing the next random point, then I am choosing this distribution, that how should I throw it. So this particular distribution, it can be anything. Right now I am choosing it to be Gaussian. This is known as the proposal function. Okay, so these two terms we have come across till now: initial point, proposal function. Now I want to talk about this. Instead of going, let me just specify this thing. Throwing a random number independent to each other, this is known as Monte Carlo, I am saying. But we are not doing Monte Carlo, we are doing Markov-Chain Monte Carlo. Now the thing is, what do we understand from the Markov chain? Markov chain is nothing but either a collection or a chain of random numbers. The way you are throwing the random numbers, that's a simple chain. But there is a very special property, a single chain of random numbers. And I'm saying chain of random numbers, you understood now? Random numbers you are throwing, that's a distribution of random numbers, 100,000. But how the Markov chain random numbers are different from the simple random numbers is as follows. If you are throwing a Markov chain random number, in that every data point, every random number that you are going to throw, that is going to have the memory of its previous steps, but only previous steps. So what I am trying to say, if I am standing here, now I can go, it's a linear space, I can go either in this direction or in this direction. But what I am doing when I am taking my next step, I am carrying the memory of my previous step where I am standing. Okay, but the moment I'll reach here, I'll not worry about my previous. The next step is going to be based on my this position. So it's not. So just try to be very clear about it. In Markov chain, when you are throwing random numbers, every random point is going to carry the memory of its previous step only, not before that. So if you have a collection of numbers in such manner, such chain of random numbers is going to be called as Markov chain. And if you are throwing those Markov chain numbers, then it's Monte Carlo. So it's the Markov chain Monte Carlo. So you are creating random numbers in a Markov chain manner, and then throwing them. That's all briefly you can conclude or say this is the Markov chain Monte Carlo. If you'll see in this particular one, I have chosen X node. Initially, I have to start from somewhere, but when I'm throwing the next data point, I'm saying this is based on the distribution. I'm defining a proposal function. I'm not throwing the next second X1 randomly. If I throw it randomly, it's going to be a normal random number that it will fill the whole space, uniform random number. But now what I'm saying, when I'll throw the next random number, that is going to take the mean X node and certain variance which you can give on your own. Okay, so just choose certain sigma for a while. So that's why, because it's dependent on the previous position, that's why I'm going to call it Markov chain Monte Carlo. Is it clear to everyone? Are we clear with this? So that's what I'm doing. Now, the moment I'm going to choose, again, same thing, it can be go this side or it can go this side, but let's say it is going over here. So let me call it X1. Corresponding to this one, let's say this is P0, this is going to be P1. So we will try to write down an algorithm in such a manner. If you define something called alpha, I'll define it. Yes, ma'am.
If you do have to redefine proposal function every time.
No, ma'am. We'll define a global diff function, but every time mean will be the previous position. So mean will keep changing.
But function is
Function is going to be same. You define the proposal function for once. In general, there are mathematical proofs that Gaussian a bit preferred, but this is not necessary that you choose it to be Gaussian. In certain problems where you are going to have a distribution which is biased, because see, if I am considering it to be Gaussian, I am saying it's going from minus infinity to plus infinity. But if you are doing an analysis in which you, let's say, some exponential function in the positive quadrant only, then obviously there is null probability that your any point can be in the negative. So in that case, you have to choose or you have to work or modify your proposal function, but that will depend on problem to problem. You have to take those decisions. Right now here we'll discuss about the Gaussian, because that's more like very much useful, or comparatively you will find the use of Gaussian very prominent in the
We
literature.
retain the memory of some finite number of previous steps.
No, only the previous one, single point.
But what if we have said?
So then it will not be Markov chain. Those different kind of chains are there. So yeah, then the method will get deviated.
There are techniques.
Yes, sir. Then there are techniques. Am I clear on this till now? So now the algorithm is very simple. What we are saying, alpha we are defining. We are calling it P1 divided by P0. So there are two possibilities. If it is going in the direction which where probability is larger, so then alpha can be greater than or equal to 1. Yes, it must be greater than 1. So is very rare. If the next point is also going to be the mean point, probability is very, very less. So if alpha is greater than 1, what I do? Because those are function of x. Both of these are function of x. So I'll choose x value. Now if I am choosing x value, now I'll put the proposal function on this given x value and draw a new Gaussian, choose the next point. In the acceptance rejection method, if alpha was less than 1, what we were doing? We were rejecting it straightforwardly. But because we were sticking in the local maxima, this time we are not going to choose it to be less than 1. Instead, we are going to say if alpha is greater than a u is a random number between 0. What can be value of alpha? It will be 0 to 1 in the case when it is less than 1. So we compare this alpha with some u. U is the uniform random number. Okay. So u is, if alpha is greater than u, so this number, let's say for example, if you have, okay, then you are going to accept it. Sorry, 1 second. You are going to accept it, and if alpha is less than u, 0 to 1, uniform random number between, then you are going to reject it. Let's try to take one case. Let's say you are throwing two random numbers. One is going to be, first one P0 is going to be some, this alpha is turning out to be some 0.95, let's say. You divide to P, this is going to be very close, because P1 and P0, they are not going to be very far. even if it is going to be less, it's not going to be suddenly very less. So it's going to be very close to the one. When you will divide them, most of the time this difference is going to be 0.9, 0.95, something of that sort. Now you will, instead of rejecting this point, you will create a independently, you will create a uniform random number between 0 to 1. So then, what is the probability that the random number that you will create that will be larger than alpha or less than alpha? Can you tell me? If alpha is 0.95 and I'll create a new random number between 0 to 1, what is the probability that the random number u that you will going to create, that is going to be greater than alpha or less than alpha? 95%, because it's a uniform distribution. 95% it's going to be less than alpha. 5% time it's going to be larger than alpha. So what I am trying to do, if I create this value turn out to be 0.87, I don't know what it will. Every time you run it, this will be something different value. If it is 0.87, I'll reject it. If it is 0.97, then I'll accept it. Means when you are taking the new step, now 95% you are asking it to reject, but still there is, you are giving it 5% probability that it can move ahead even when the numbers are, probability is not very much acceptable. If you keep repeating this exercise and eventually if your distribution after certain point you'll throw 1000 points, then 950 points are you are going to reject if it is continuously in that region, but 50 points you are going to accept as well. If that is the case, those 50 points will give you a channel through which you have a finite probability that you can come out of that local maxima and you can go into the region where the another maxima or the another global maxima might be going. So you'll not stuck somewhere. You are having a finite probability to approach or to kind of scan the domain which is not suggesting this acceptance rejection algorithm. Okay, is it making sense? So this way of doing the exercise, this is the algorithm. That's all. This algorithm is known as the Metropolis Hastings algorithm. Okay. Is any issue with this? Fine. Let us try to write down a simple code. I'll just try to show you the code. I hope I am assuming that you have done a little bit session on the Python and you must be familiar with the Python syntax. Okay. So just have a look on the point. What I am doing, I am defining, just forget about this a naught. So just see this float. This float is -3 to 3. So I am choosing an initial point. Okay, it will see this is -3. I am choosing an initial value. I am choosing this value to be somewhere like -5. Okay, this is my initial point. As 25,000, I have chosen that I'll throw 25,000 random points. Okay. Forget about it. Let's make it 0 right now. I'll talk about this term later. Forget about it. T equal to 0, I'm doing this one. So just have a look on this. I'm saying a new. A new is the x value. Every new value I am defining a new. So this is a naught. A naught plus np dot random dot normal. What is this command for? This is for creating a random number which follows the normal distributions. So what I am doing, I am starting with -5. I have shown you a naught is -5. Now I want to throw the next a new. I am calling that.
What is S?
S is the number of steps now. Oh. So it's a for loop on S, means it's throwing 1, 2, 3. So that's an iterative process. Okay. So every time I am creating a new a value which is going to have mean to be a naught and certain variance with Gaussian distribution. Right now variance as a user I have decided I am giving this 0.1 variance. You can play with other variance, make it 0.5, make it make it 2. Try to see what is happening in that case. I'll discuss it as well, but you play with it. I'll give it to you to play. Then if it is the case, I am calculating that alpha. The distribution that I have named, I have defined that particular function to be target distribution. So if you'll see, you know how to define the function in the Python. Given the function, define the function. That's I'm leaving for all of you. The name of the function is target function. I'm calculating target function at new value divided by the target function at a naught. Okay. Then I'm creating a u, which is np dot random dot uniform between 0 1. So u is the third parameter. Three values I have calculated. Now I'm saying if alpha is greater than u, if I want to write down my code, which is alpha is 1, greater than 1. This is acceptance rejection algorithm right now. If alpha is greater than 1, what I am doing? I am adding t equal to t plus 1, and then I am appending these points in the chain. You know what is the append command? Have you done the append command? So those points you are accepting, you are appending in a list. Append command works for the list, not for the arrays in the Python. Okay, but we are working in the list only. Okay, then if the point is accepting, you are adding it. If the point is rejecting, only if alpha is greater than 1, you are keeping track of it. If else a note is a note. If else you are rejecting the point, you are again choosing the same mean, throwing the next point. So until unless you will get a point which is kind of forcing you to go towards the maxima, you will keep throwing the chokes or throw the random numbers. Okay, that's what you are doing. Okay, if I run this, should I run it? Just give me 1 second. Let me see if internet will allow us to do that. Just if it will not allow us, then you have to run it on your own. Okay, fine. So these are the libraries. NumPy library, so all of you must be familiar. Pandas is for data, for doing any sort of data analysis. Plotly. So when you try to do any sort of plotting in Python, there are 3 libraries. Most popular one is the matplotlib, which most of you do use. Then second one is seaborn, and third one is plotly. So matplotlib is not very helpful in using in interactive plots. You might have seen these plots where are very interactive, like you can scale, zoom, 3D, rotate them, all those kind of things you can do. If you want to do that, use the plotly library, but it's up to you to figure it out. Okay, so then matplotlib library are as well, animation and all these library can be very useful. I have ran this one. If I am running it, this is the distribution. Now I am running this program. Okay, and instead of running it for 25,000, I am running it only for the 2500, so that it will run fast. Okay, what is it saying? Target is not defined. Okay, let me just run it. Yeah, target defined. Program is very simple, just for loop and if else loop. No, nothing special about the program. Okay, so I have run the program. Now, once I run the program, it will create. So I am creating this chain. A chain. This is a list of all the accepted numbers which I have accepted, and the other rejected one I am not keeping track of that. I have thrown 2500. Let's see if I am throwing 2500 and choosing the acceptance rejection algorithm. Let's see how many points we are accepting, because all the accepted points we are lying into the A chain. You can, okay, so if I'll plot it like this, let me run it again, it will see. This is the list of all the numbers which I have accepted. Okay, so -5 I have chosen. You will see these are going -4.8, -4.7, -4.6, and I am just going towards the maxima because my maxima was somewhere on the positive side. Now, if I try to find out the length of this one, I'll also define some length. How many points are going to be there? I am defining len of HN. And then print. So Python is case sensitive, please do remember that. See, out of 2500 points, 73 are going to be accepted. So you can see you are throwing so many points, most of the points it's rejecting, only 73 it's accepting. Now, you might have heard this word called Markov chain, because we are choosing the numbers in a special manner. If I'll plot it, this is generally we call it Markov chain. What is we are plotting? On the x-axis is the number of points. We have 73 points I have shown. Those points, and on y-axis is the value of x. So I am calling it the chain. Okay, Markov chain. But let's try to focus. See, if I plot it on the distribution, I started from somewhere -5. Let me try to plot it on this distribution only. See what is happening. Wasn't it we expecting? We started from -5. You are approaching toward maxima region, reaching there. The moment you reach onto this peak, local maxima is stuck over there. Now your algorithm is not allowing you to go over there. Now what I did, if you, this is the acceptance rejection, I'll go back to my code, I'll make a change, I'll just, instead of alpha greater than equal to 1, what I'll do? Now I'll going to give it some probability through which it can escape this region. I'm going to say u, sorry, small u. Fine. This is the only change I am making. This is the conversion from acceptance rejection to metropolis testing. See how is it? Now I am going to, so every time I am going to throw, if the value is 0.95, so I am allowing 5% time, I am allowing it to go into the other region as well. Okay, with this change only, let me run my program. What is the answer? Out of 2500 points, 2200 plus points you are accepting. Okay, and now if you'll see, you can have a look on this chain. These were only 73 points on the x-axis, you will see. Now if I plot the chain, these are 2200 points. Okay, then further if I try to plot it on the distribution, just overlapping the points on the distribution, it might take a while because the number points are quite large, and I'm using the plt.scatter. Are you familiar with the plt.scatter? It's not a very good way of plotting, but easy way of plotting, I'll say, because it do take a lot of memory and a lot of time to plot. Let's wait for a while. So what are we expecting meanwhile? Yeah. So now this is allowing you to go into that domain. It is reaching. So maybe when it was on the local maxima, with very less probability it might be moving forward, but the moment it reaches somewhere here, the moment it reaches somewhere over here, immediately it picks up, and then immediately it will keep reaching. Now even when it reaches on the global maxima, our algorithm is not going to stop, because still you are, yes please,
Rejecting those points.
can you repeat please?
You said that alpha less than 2, we are going to reject the point.
Yes.
It is not.
No, it's rejecting.
But then why it hasn't stopped in the maximum?
Then that's the problem. If it is going to stop on the global maxima, how do you know that the given maxima is the global maxima? In the metropolis algorithm, you will keep, even when you reach the maxima, even then you will be keep exploring the neighborhood. Now, if your neighborhood is not going to give you the chance to escape, it will keep coming back. You are only giving 5% chance for the distribution to move ahead. Remember this thing. You are not giving 95%, you are rejecting it. So you can have that comparative analysis in your mind. Okay, so you will keep doing, but you will not kind of stuck over there, because that was the problem. Now let's say if I want to get a accurate result, what I'll do, instead of 2500, if I'll throw 5 lakh points or 1 million point over on this, then you will see out of those 1 million point, there are always going to be instances where points will be going into this region and this region, but maximum number of points they are going to kind of accumulate over the maximum only. 95% times they will accumulate over here, and 5% time they will be exploring the neighborhood space. So if you plot that such a large number of distribution, you will see here there will be the accumulation of the data points. Fine. Is it making sense? Now it is very important that you don't believe on the, because see, in 1D you can see it. In 4D, how would you know that what is the whole space is working? In 5D, you cannot plot it. Right now, we are able to visualize this because we are having this particular distribution or particular plot before our eyes. But in the unknown distribution, it would not be possible for us. Okay, fine. Now, here comes a very interesting analysis, and some of you are asking me about the data. How do we quote the result in the papers? Over here, you will see. This is a collection. This is not a Gaussian distribution. Yes. Now, in Gaussian distribution, generally, when we try to quote the result, if I'll give you 1 million values which are accepted over here, and those are Gaussianly distributed, you will immediately calculate their mean. Then, obviously, you know the formula how to calculate the variance. From the first years onward, you will keep calculating the variance. You will calculate the variance, and then you will quote your result. This is the distribution with this mean plus the given variance. But this variance and this concept do hold only for Gaussian. This concept of 1 sigma error, 2 sigma error, this holds only for the Gaussian. So now when we have this kind of distribution, how to quote the result, how to justify, and how to even see what kind of answer we are getting. Okay, so let's try
Why
to.
does it stop here? Why doesn't it explore for more peaks further down?
So see sir, because reason being, now here comes the role of that parameter sigma. Here if you see, when I was choosing my proposal function, if you see, I was choosing this proposal function to be 0.1. Now what I am saying, if my value is let's say 2, I am allowing within 1 sigma, I am saying the probability for it to move from 2 to 2.1 and 1.9, that's very large. But instead, if I want to scan it a very large space, what I'll do, instead of 0.1, I'll make it 0.5. Then it will is going to scan a very large space. Even here it's a problem. When we choose the sigma value, think about it. If you choose this sigma to be very small, very small means 0.001, then the pace or the speed with which you will be moving towards the maxima, that will be very slow. And if it is going to be very slow, you will be taking finite time to reach to the maxima. That will be very, process will get redundant, or you have to invest a lot of computational power. But if you are going to make it very large, then your maxima, it is very much possible that you are in this local maxima. You have given this probability to be very large. It will just jump to the global maxima. It will go into the some other domain. So it's very crucial for us, and that's one of the limitation. We'll see how can we get rid of this as well. So if someone will ask what is the limitation of Metropolis testing algorithm, it is we have to decide on this sigma. We are supposed to, as a user, we are supposed to take some call what should be the optimum value of this sigma, so that your proposal function should be such that it would not jump over the maximas, it should not be very large, it should not be very minimum. But that's a user dependence, and that's not good from the point of algorithm. There are some advanced algorithms where we'll be talking about EMCMC method that's based on something called Z sampling approach. So that get rid of this issue as well. But even when you talk about, those of you are familiar, this is Metropolis, we'll talk about Metropolis testing. There is something called Gibbs sampling as well. All these algorithms do have this issue. You are supposed to decide on this sigma as the user. So that's a limitation. With that,
Where
yes,
did
sir.
you define your small u?
One second. Small u.
Small.
So this is the uniform random number that I am creating, with which I am comparing whether I am accepting or rejecting it. So every time I am choosing, this alpha will be somewhere 0 to 1. So I am, with the help of it, I am either accepting or rejecting. Okay. Now how you will play with it? I'll give this code to all of you. Discussion tomorrow is going to be extension of this one only. I'll just take 2 more minutes. And the extension of this one we are going to have. Now tomorrow I'll extend the discussion for the 2D, and then with the data how you play with it. But it's important and you understand this properly. Choose different sigma, run it. It might take some time. Run it for very large number of random points and then plot. Okay. Now what I was trying to say, I was saying, you in the papers, or when you do see research papers, you might have, in the when people started working on this, they used to give these chains as well, this kind of plots. They used to give these plots as well. But now you will see they will just give you the result. Okay, this is the mean, this is the variance, and you are supposed to understand that. Over here in this one, if I'll define it to be how to quote the result corresponding to that, just try to see what I might have done. This is the random number. If I try to plot a Gaussian on it, if I take the mean and try to find out the variance of it, this is not my plot. Obviously, it's not a Gaussian. If I quote my result as with the understanding that I am trying to find out the mean and I am trying to find out 1 sigma variance, then that's not what happening over here. So that's why over here, whenever you have Markov chain, we do not quote results as the 1 sigma error or 2 sigma. In paper, you will literature it will find, but we rely our results are going to rely something called percentile. Okay, so what does percentile mean? Let me just give you a brief overview. What I am doing, if I am having a distribution something like this, and these are let's say 10 to the power 6 points distributed, what I'll try to do, I'll calculate their median. Okay, I'll calculate their median. So even in our distribution you will see sorry, just one second. Even in our distribution you will see a large number of points are lying in this region. You will see large number of points here and less number of points. When you will plot it individual, you can just do that analysis, try to figure it out. But your median automatically, if the number is very large, will be somewhere like here. Median will lie over here, because even when it's going to be very large number, it will revolve around. So the moment you will get rid of this points, initially it will hardly take 5 to 5,000 points to cover this region. Beyond 5 to, or you are running it up to 5 million, all those points, they are going to lie in this region only. Okay, in back and forth they will keep oscillating. So if you calculate the median, then it is going to be the here. So when you try to quote the result median, that is going to be, this is going to be your x naught value, sorry, x best fit value. How to quote the error now? Now instead of calculating the mean and median, what you will try to define something called percentile. Corresponding to this mean, you will define something called 1 sigma, the region which is going to be 68%. The region in which this is going to be 68%, means 34% points should be in this region, 34% points should be in this region. Am I visible? Is it? Yeah. Now one thing, try to remember one thing. If you are choosing median and you are seeing corresponding to this median, on the left hand side I am going 34% points. So, and on the right hand side I am going 34% points. Now 34% of the total collection. Now it's not important that these number of points, the region x value, if this is x best fit, so this x1 sigma I am calling, that you are going in this direction, it should be same. It can be different in both direction. 34% point might be lying on a longer range in the this direction on left hand side, or on the different x value on the other hand side. So the region that you are going to have over here, you are going to define as the sigma minus, and the error that you are going to have, this one, you are going to call sigma plus. So that's why you will define a best fit value which is going to be median value, which you will call it the best fit, and you will give this plus and minus error separately. Okay, here you cannot give a common mean. That's why in the papers which you will generally see, if the error is given, because most of the analysis, most of the people are going to quote the percentile error only in their analysis. All these inbuilt library, EMCMC or Cosmo Hammer, or all the whatsoever library we were used to have, they do calculate percentile only, and that's why the result you will see, they are going to say 0.05, let's say here 0.03. So this is the meaning of this plus and minus error bars. On one hand side you are going, so you are defining. Now why 68? This again we are taking it from Gaussian. We are saying because in Gaussian 1 sigma corresponds to 68%. So that's why as a statistician we have to choose some number. So we are kind of biased towards the Gaussian. All the statisticians used to like follow the Gaussian, take it for granted. So we have chosen that number 68 from there, and now we are divided 34% point this side, 34% point this side, and that's how we are defining our percentile of 1 sigma. Yes.
So I was asking that you have chosen the one Gaussian with maximum median. But what if you have 5 Gaussian like this and
5 Gaussian like this? Can you? This is not Gaussian. Huh? This is not Gaussian. So if you
are assuming it to be
oh,
Gaussian.
is it not changing over there? I'm changing it here. It's kind of jammed. Is the session going on? It's not changing on the screen.
Okay. Actually, he said, oh,
so yeah, let me answer to your question. This is not Gaussian. This is a random distribution. Could be anything. Yes.
But if, yeah, in that distribution, if we assume this, that one with a smaller piece, with the local maxima,
Yes.
there, if we assume it is having a
he's saying net
median
nature.
and what if
it will not. It will not. See what I'm trying to say. That's why if you are going to create a chain which is going to have very less number, if you are running your code by using only 50,000 points, then it is very much probable that a large number of points will be.
चल रहा है, according to me it's working.
But it is zooming and.
अच्छा, it's zooming in and out. अच्छा, I thought you were doing it. ये कौन
No,
कर
I was
रहा है?
not doing it. Okay.
Achha.
So now over here, if you see.
Maybe
these
somebody is doing
points,
it.
If you choose very large number of random points that you are throwing, then your result is anyway going to be very, very long. Then you cannot rely the analysis. Then your point that median will be lying somewhere in between. It might lie in a minimum as well. Because you are choosing, if you are choosing, let's say 5,000 point only. So 2,500 points it is having in the roughly, let's say in the local minima. And then 25 around is having in the local, sorry, global maxima, then you will take the mean, it will come somewhere in the minima, then you will say, okay, it's a completely absurd method of working. That's why, whenever you are going to use Markov chain Monte Carlo, your focus should be that depending on the computational power that you are having, choose the largest number of data points. If you can choose millions, then choose that. Okay. We will see how can we modify it. What we'll be doing it running multiple workers, but not today. We'll do it tomorrow. Okay. Is it making sense till this point? Yeah. Yes, please.
So here we see one local maxima and one global.
Yes.
And we don't know what the data is, right?
We don't know the what.
So if suppose it comes out to be two same global maxima.
Yes.
Then how to calculate the median?
Here this is a mathematical algorithm. Okay.
Right.
This is not biased with what do we want. It's going to give what is true. You are throwing random numbers, it will calculate some value. What it will do, it will give you a distribution. Now, those of you might be working in the cosmology, might have seen those like histogram, those corner plots. Have you seen? I'll show you tomorrow as well. Those of you are not familiar, then you will find out the distribution is going to have two kind of points where there is going to be a large number of density of points. Then you have to explain that. Explanation will be an issue. Then calculating the mean will be an issue. Giving the variance will be an issue. That will be a problem. I agree. So then you cannot give a single mean because you are having two maxima. Then you have to interpret whether it's the issue with your data, with your model, or something new is emerging from your analysis. That would be the mathematically you will get a distribution of random numbers following certain math formula, some certain rule. Definitely, however distribution you will give, it will behave in that manner. But how you will interpret it, that will be an issue.
My point was we get 2 sigma plus and 2 sigma minus in that case.
Again, then issue would be whether you will choose the mean value that we do have, whether median would be a good choice to make over there or not. That's why whenever you try to study in paper in cosmology, be very cautious about how the author are kind of quoting their results. Whether they are calling it mean, what is kind of distribution they are having. You need to be very particular and very skeptical about it. And in cosmology, I can personally tell you around 8 to 10 papers which people are saying this is the 1 sigma error. Calling it 1 sigma is also not correct. I think it that way, but in literature you might find people saying it 1 sigma. Okay, because 1 sigma, the moment I'll say 1 sigma, it gives me a picture that I'm relating it with Gaussian. I should say it's a 68% percentile region. That's the correct terminology. But if the whole community has accepted it in that sense, so one can't change or one. But when you are kind of reading the paper, you must be aware about it. Okay, even if someone is quoting it. That way.
Sir, and adding to his question, can we go for the one with the minimum variance?
Minimum, that's sigma.
Yeah.
Sigma you are saying?
Yeah.
So you can choose it. Choosing it to be minimum will be to be very small. It is a good choice. But if you are going to choose it very small, then your computational power, even 1 million or 1 billion point will not be sufficient to scan it. When I will be talking about higher dimension, here so it's easy. It's 1D. Here so if I do the analysis, I would prefer to zoom the plot and find out the maximum. That would be easier for me. I can plot it and look at why I'm doing this exercise, because the way I'm going to get my result, if I'll just show it to you, the result that I'll be getting here, you run it, but I'm getting 0.19. This is my result over here with this algorithm. Okay, sorry, not this one. 1 second. Yeah, this kind of plot. I'll talk about it in detail tomorrow. My value is 0.30. Okay, this is what my answer is. I'm saying the value is 0.30. This is the median value with error. Just have a look on the error. 0.48 minus 0.72. Mean value is a small, error is so huge. You can see because I'm working with only 2500 points or something. So with 2500 points, you cannot expect your result to be good. Let's say wrong result. And if I'll go to my plot, so this value was 0.3. Why I'm doing this? You would say, okay, I am having this plot using plotly. I have plotted it. I can see. I'll zoom it. Well, I'm getting a better result by using just simple plots. Why I'm running this? But right now here purpose is not to do it in 1D. 1D is not going to be good method. But the moment you will go into higher dimension, you are not going to answer. In the previous class, someone asked me about the gradient descent. Yes? Yeah. Now to answer to this question is the following. See, one of the biggest challenge in the computational one, even in the gradient descent, all these methods do scan the whole space. Means if you want to apply the gradient descent, then you will try to calculate the value on each and every point in the space. Now computationally that's very time consumable. Over here even 2500 points you are getting a result. If you throw 1 million point, result will be better. But if you run iterative loop on your gradient descent and you all try to scan a 3-dimensional space each and every value, with gradient descent it is going to be extensively computational. It's going to need a lot of computational power. Okay, that's why when you know why I'm saying this, let's say you are doing cosmology, then you know matter density that is not going to be beyond 1, total matter density 0 to 1. Then you know that your region is going to be 0 to 1. You can put some condition that my values should not go beyond 1. But let's say you don't know anything about the data, then any value can be in the space. Then you have to space the whole xy numeric space in which your distribution is there. Then it would become very difficult. You cannot scan it because it's based on probability. It will keep moving towards a maxima, a global maxima. It will approach to the maxima region very rapidly in comparison to your gradient descent. So gradient descent, if you have a limited space in which you are supposed to search, then gradient descent is way more better than this. Then you'll use it. But the moment your space is open, you don't know what is the range of x, what is the range of y. Then so you have to rely on this.
So if we increase the step size,
but then if you will increase the step size, then there is always a probability that you might miss some local maximum minima in between. Yeah. So try to do it. Means I'll also give some problem today. Try to do the surface integral, volume integral by using it as well. I'll try to show it to you.
Yeah. So let's thank Akshay for a great talk. He is around with us for the rest of the thing, so you can feel free to this thing.
Most probably by evening I'll share some on email. Then
Yeah. You have the emails.
email.
मैं share कर लेती हूँ. I'll give you the thing. Okay. So we need to rush for lunch because lunch is ready, and 2:30 is the next session, which will be on time because that's an online session, right? So please, have your lunch fast, come back fast, right? And today's a long day, so eat well. Yeah, preferably come back by 2:20. The sooner the better. Oh, combined mail में है. You have a mail which has all.
Okay, ma'am. So
Yes,
yes, I'm receiving all the mails that you are sending.
very good.
If there is no it will voice आते रहेंगे. It will not give any.
What is that called?
There
Oh,
will
I need
not
to
be
1
any
minute.
collection. So